This is a briefing on the module Theory of Computation. So what is the motivation behind this module on Theory of Computation? What precisely is an algorithm? That begs the question towards formal model of computation. Do algorithms always exist? What are the capabilities and limitations of algorithmic computation? And how do we establish them? What is possible and impossible to compute should be independent of the model of computation. How can we reason about computation? So, this leads to the question on what is theory of computation and why we go to theory of computation. By studying this subject, we get to determine what can and cannot be computed, how fast, and using which type of computational model. It helps us to understand how efficiently problems can be solved using algorithms on abstract or mathematical models. You may ask, why theory when we do wish to have hands-on and practicals to learn things faster? However, we should understand that theory is relevant to practice. Theory of computation includes four major topics that includes formal languages and grammars, automata theory, and computability theory that defines what can be done by computers, and lastly, complexity theory that defines what can be done in practice or reality. Theory of computation is inherently abstract and mathematical. Practice through solving problems is essential to learning this subject. So, the first topic on theory of computation discusses about language and grammars. So, a formal language is an abstraction of the general characteristics of a programming language. Whether we communicate with machines or communicate with people, we use a language. So, with machines, we use programming language, while we use natural language when we communicate with people. So, to verify whether the language that we use, irrespective of a programming language or a natural language, whether the words and sentences are following the grammars of the language, we need to define rules. So, grammars basically are concerned with the specifications of syntax and rules. So, in particular, this topic will discuss how do you indicate a machine, what programming language instructions are legal and which are not. The next topic dwells on automata, that are abstract models of a computer or mathematical models of computation that helps to reason about computation. An automaton, in other words, a machine, an abstract machine, has all the features of a digital computer. It can accept input, produce output, and has no or limited memory, can make decisions in transforming the input to output. In particular, the key role of memory is emphasized in three different approaches to memory, being none defined by finite state machines, a single stack, a push and automated, and using a semi-infinite tape defined by a Turing machine. Finite automata practical examples include text processing, compilers, and they are widely used in hardware design as well. Another model, the context-free grammar, is used in programming languages and artificial intelligence. Computability is concerned with the fundamental limits of computation, where we classify problems as being solvable or unsolvable. In particular, it may be surprising to learn that there are some problems for which it can be proved that computers cannot solve. Computability is used to develop theoretical models that eventually will help to develop the actual algorithms of.
Hello, good afternoon. I'm Jing. I'll continue the lectures. Okay, next we talk about complexity. Complexity is concerned with measuring the cost of computations. The focus is on the maximum execution time. Classified problems according to their difficulty or efficiency in terms of time. In reality, they are problems that cannot be solved in any reasonable time, no matter how fast the hardware improves. So the important application here is cryptography. So what makes some problem computationally hard and others easy? This is the main questions of complexity theory. Next, we move to cryptography. Cryptography is concerned with encrypting informations so that no unauthorized person can read it. The main technical issue is how we can be sure of this. The answer for today is to use the method that no one can solve it in reasonable time. But in futures, quantum computing will make today crypto algorithm obsolete. That will be the next topic for our next discussions. Okay, as a conclusion, the specific skill covered today is to read and write grammars, passing and deviations, design automatons, compare and analyze different models of computations, analyze algorithmic complexity, and last but not least, discussions on crypto algorithm, including public key cryptography, namely RSA algorithms. Thank you. If you have any questions, you are most welcome to ask.